In the real world, policy-based routing can eat your network alive because it's very powerful. You get a lot of control. And I am reminded of the Spider-Man quote. It was actually Uncle Ben who said, "With great power comes great responsibility." There's great power at your fingertips with policy-based routing. And let me show you how that power can pose problems for us. So what if I've got a classic PBR setup like this? I've got all of my traffic normally routed to 666.6. Okay, so ISP1. That's our primary ISP. But in this situation, I want to override that, and I want only some traffic to go through ISP1, and maybe I'm willing to give inferior service to the 1-2 network. In this case, what I'll do is this. I want to change that. So what I do is I set up policy-based routing like this. I'll build an access list looking for the 1-2 network that I want to override. I will match it and set the next hop to ISP2 and apply it to Ethernet 0. Looks good, right? On paper, it looks good. But in reality, this router probably has connectivity to other networks, right? Probably has connectivity to other networks. And let's just say we got the 10 network out here. And this router has connectivity to the 10 network out there in space. Okay. Is any traffic able to go through Ethernet 0 to the 10 network? Not based on this config. Why not? Because we're routing based on source and not based on destination. We've got a problem on our hands. We've broken connectivity to the 10 network. So what do? What we say is, I need to alter my PBR config so that instead of applying to all traffic, only apply to default routed traffic. And there's a way to do that. There is a way to do that. Instead of IP next hop, we will say IP default next hop. And if you inject that subtle keyword between the IP and the next hop, you now have restored connectivity to the 10 network. Here's why. It says only apply PBR to traffic ingress on E0 now, or only apply sequence 10's action if you would normally be default routed. And we would apply or think that we're using default routing normally to get to these two ISPs. So if you are bound to maybe the public network, you'll still be overridden, or PBR will work as desired. However, if you're trying to get to the 10 network, we'd presumably have specific routes and not default route them. And so therefore, we catch ourselves. It's a net for us to say, oh, I would normally route to ISP2 if you come in on Ethernet 0, but wait a minute. I'm just going to double check myself and say, do I have a specific route? And if so, then this does not apply. This is a powerful configuration, and using it will allow you to have your load balancing work in a desirable fashion when you are thinking about overriding your default routing infrastructure. So be very careful when you apply PBR to the real world. I'd like to walk you through a great example of the set IP default syntax in a great textbook example. Here's what's going on. 1.1 goes through ISP 1. 1.2 goes to ISP2. Here is how to pull that off. Build in your access lists. Set up your route map. Let's look at that. Sequence 10 is looking for 10.1. Excuse me, 1.1. We're using set IP default next hop, saying only use this sequence and only do what we're saying to do if you would default route that traffic. So this is going to send 1.1, traffic coming from 1.1 to the ISP with this next hop IP address. The second sequence, sequence 20, will say 1.2 is going to go to 7.7.7.7. Now the final sequence is really interesting. And what it says is send traffic to the null zero interface. Setting a next hop IP address is safer than setting an exit interface. And setting an exit interface of type Ethernet will enable proxy ARP, so don't do that. But what are we doing here? We're saying set default, so we're using the same default command, and we're saying shoot the traffic out without consideration of the next hop address out of this interface. But what is the null zero interface? The null zero interface says drop it. So what are we doing? We're doing spoof mitigation. Let's say these were the only two subnets that we wanted to send to the internet. If someone is spoofing an IP address, they may be spoofing an IP address that we don't own, that doesn't exist or should not exist in our network. Therefore, outside of these two subnets, if you aren't matched by sequence 10 and sequence 20, then drop the traffic if it is trying to get to the internet. Very powerful stuff. And now all we have to do is apply it to the receiving interface, and we have just set up a powerful load distribution utilizing two different ISPs. So to review, we just said 1.1 is going to go to ISP1, 1.2 is going to go to ISP2, and all other sources, if trying to go out to the internet, are going to go to the garbage can. They are going to go into the abyss. Okay? Very powerful. Know your verification commands when it comes to policy-based routing. Show IP policy displays which interfaces have PBR enabled. Show route map shows you the logic, and it's semi-readable. Let's say it's readable. We say the route map equal access, which has a sequence of 10, which is a permit statement, says look for access list 1, which we don't have further enumeration of, and if you match that, set it to the next hop IP address if you were default routing it. But what's really great is we see the number of packets that are matched. And oh yeah, the number of bytes. I don't care about that. I care about the packets. That tells me something is working. And then sequence 20. Looks like I don't have any packets matching that one. And sequence 30 is sending traffic to the null zero interface. This is spoof mitigation we sometimes build in to a PBR config. And if I saw matches for that one, we'd want to research exactly what's going on. Maybe plug in a sniffer, see where they're coming from, turn on debugging at that point, debugging being pretty impactful, but we'd want to research it.